whose title is Thematic Individualized Treatment Rules Without Individual Data Analysis.
I'm sorry, I can't see very well. I'm sorry. Should I blue or not blue?
Yeah, I think
Just think I understand.
Blue is good?
Yes.
Okay, sorry.
No?
Sorry,
Oh.
I'm now revealing just how bad my eyes are. Sorry, I can't. Gotta click something. Thank you so much for the invitation, Alina. I'm delighted to be here today. So today I'll be talking about something from my main research area, which is precision medicine, trying to learn about individualized treatment rules, how to allocate treatment based on individuals' covariates without having to share individual level data when we're running studies with multiple centers. So my roadmap for today, I'll talk a little bit about what precision medicine means in the statistical literature. It's a term that's used often. I think at one point Obama had a sort of moonshot type thing for precision medicine, but there are just lots of different terms or ways that precision medicine is used. So I'll explain what I mean by precision medicine and what's typically used in the stats literature. I'll talk about a doubly robust regression-based method of estimation. Doubly robust just means that we specify a couple of nuisance models, but we only need to get one right for our estimation to be consistent. So it's not really doubly robust. You can't get two things wrong, but we specify two things and can get one of them wrong. And I'll talk about a couple of different candidate approaches to preserving privacy. So when we're working in this multi-center data setting where we've got data housed in different repositories, but we want to protect the privacy of the individuals who have their data at these different centers, how can we do it? And then I'll show a couple of case studies. So how to individualize warfarin dosing when we've got a continuous treatment, and how to individualize frontline antidepressant treatments when we're just looking at binary treatment options. So my great colleague, Jim Hanley, started saying many years ago that he had reached the age where he was looking back. And I thought that was very sweet. And now suddenly I've reached the age where I'm looking back and reading some old papers. And I've been reading a lot of Sir Austin Bradford Hill lately, because he is really one of the first thinkers in medical statistics and epidemiology of a lot of the ideas in causal inference that I rely on, although they tend to be, I would say, less formal or less mathematical than much of the more modern causal inference literature. But I came across this quote and I really liked it. It said, the medical statistician recognizes and is familiar with the pros and cons of that difficult question. Should a fixed dose be given to all patients, or should it be allowed to vary with the apparent needs of that patient? And I think it's particularly interesting in a causal setting because a lot of causal inference is focused on average treatment effects, marginalizing or taking integrals over the covariate distribution. So really trying to see what happens if I give something to my whole population. It's more of a policymaker perspective, but the policymaker is not the patient, right? I don't care as a patient what happens to the population. I care what happens to me in my particular age group, my particular family history. I might want something that varies with my needs if that's better for me than what's good for the population as a whole. So the other quote that I like to pull out from David Sackett, who is an American, but we call him a Canadian American because he spent some time up here. He was actually the first to define the term evidence-based medicine, surprisingly late. It sounds like something that's been around for a long time, but he defined it as a conscientious, explicit, and judicious use of current best evidence in making decisions, not about patients generally, but individual patients. So again, there's this idea of really caring about the individual patient and not just looking at blanket policies. All right, so precision medicine then is really trying to get at this. I'm trying to tailor medical treatments or decision-making to the individual characteristics of each patient. Okay, when I say sort of, I'm not actually talking about selecting or creating drugs that are unique to a patient. So you may have heard of precision oncology, where a biopsy is taken and 20 different combinations of chemotherapies are given to see how the tumor cells react. I'm not actually talking about individualization at that level, but rather trying to classify individuals into subpopulations. So come up with decision rules based on more macro level characteristics. It could involve a couple of genes, it could involve sex or blood pressure, but really if there's someone like me, we would get the same treatment. So we're looking at fairly crude individualization. But what we are looking for is that, and I throw up Goldilocks here because what we're looking for is the just right treatment, not too much and not too little. Okay, or to be a little bit sillier, I was watching The Simpsons with my kids because they're at an age where we can watch things that I used to watch at their age. And in this particular one, Homer was saying that his head is too hot and his legs are too cold, but his middle's just right. Right? We want to find that just right treatment. We don't want people burning or freezing. We want something that is just right for a given person at a given time. All right, so I'm working in a context then where I might have several different treatments or doses available. Patients may be switching from them over time. And often, this is where my causal inference background comes in. I usually need to account for clinician decisions. So the treatments aren't randomized, but in fact, the treatments that patients receive might be related to their outcome on those treatments. So sicker patients might get a more aggressive treatment, for example. So that can be a problem if we're trying to disentangle the effect of the treatment, right? If sicker patients get the more aggressive treatments and they fare badly, well, is that because the aggressive treatment is bad, or would they have fared badly anyway? That's what we need to worry about. So I want to then make use of measurable patient characteristics. And as I said, these can be sort of macro or sort of micro. It could be genetic or demographic. I don't tend to work in a very high dimensional setting where I'm screening thousands of genes, although it is possible. It's just not the work that I do most often. I might also be looking at clinical characteristics or medical history to try to determine what treatment to give to what type of patient based on these characteristics and when in a particular course of their treatment history. So why do I want to adapt or individualize treatment? Well, it's better if there's variability in how patients respond. Right? If we all go and fall down the stairs and we all break our arms, we probably all need a cast. There's not a lot of variability in how we would respond to that. Okay. But the second case study that I'll look at, treatment of depression with antidepressants, is a perfect example. In the US, there are over 25 FDA-approved antidepressants. They have all been shown to have moderate average effectiveness, but individual response to those drugs varies pretty considerably. And we still don't have a good handle on that treatment heterogeneity. So trying to understand who is reacting differently and being able to predict that so we don't have this trial and error through potentially dozens of different drugs. We may also be in a setting where patient response changes over time. So this could be because, for example, a patient develops resistance to an antibiotic, or they develop a tolerance to a pain medication. So even though something is working for you now, it might not work for you in 6 months' time. Okay, we may have response to one treatment informing later treatments. So if you react well to a given drug, we know to continue that drug. If you react badly, it might close off an entire class of drugs. So again, this idea of personalization and learning from our past successes and mistakes, and trying to do things like correct for compliance. That can be something that, again, informs us how to treat our patients. But again, it comes back to this Goldilocks idea. Overtreating can be bad, right? It can lead to excess side effects, excess costs, treatment fatigue, so that patients just get sick of taking whatever it is you're giving them. But of course, if we don't treat sufficiently, then we might have poor therapeutic outcomes. All right, so that's a lot of words. But this is a day of women in math. And at least some of this requires an equation, right? Or at least some graphs heading towards equations. So if we think about when we want treatment to be adaptive, let's think about some regression lines here. Okay. So what I'm showing here on the far left is just a simple regression. On my y-axis, I have some outcome where bigger is better. So think of something like a quality of life score. Along my x-axis, I've got some covariate, a candidate tailoring variable. I might try to use this to allocate treatment. And I've got a binary treatment, each of those lines representing the different levels of my treatment. So we can see in this far plot, we have no statistical interaction, right? My lines are parallel. So if bigger is better, how do I want to treat people here? Solid or dashed? Solid. Doesn't matter what the level of the covariate is. Solid dominates. It's always better. So over here, we can see there's some sort of statistical interaction going on. I no longer have parallel lines. but I still want the solid treatment, right? Over the range of the covariate that I actually observe in my patient population, it's still always better to use that solid line treatment. Okay, maybe if I'm at this end, I think, it doesn't make much difference. Maybe there would be other reasons that we might have some indifference, but based on that outcome alone, the solid line is the one to choose. It's only when we have what's known as a qualitative interaction, so our lines actually cross in the range of the covariate where I've observed, that this becomes a useful tailoring variable. Right? If I'm at the high level of my covariate, that solid line looks great. But at the low levels, I can see I want the other treatment. So that's what I'm looking for when I'm doing this statistical study of precision medicine. I'm trying to find these interactions, and I'm trying to see where it is that these lines cross, because where they cross is the threshold that helps me decide how to treat individuals. So these variables, like the one on the far right, these are called prescriptive or tailoring variables because they tell me how to prescribe treatment, how to allocate it to patients. The other two plots, not very useful. They might tell me something, they might give me better prediction of my outcome, but they don't tell me anything about how to prescribe treatment. So if we look for these types of treatment covariate interactions and use them to decide how to allocate treatment, well, we get our treatment algorithms or decision rules. And there's a whole bunch of different names for these. So in the stats literature, they tend to be called adaptive treatment strategies or individualized treatment rules. For a long time, they were called dynamic treatment rules, but that language sort of fell out of favor. In the social sciences, they're called adaptive interventions, and in computer sciences, they're policies. But it's all the same thing. We've got a state, we want to decide an action, we see an outcome. All right, so I'm going to focus on one-stage rules. So individualized treatment rules where I'm just doing it once. I'm not looking at a sequence. Okay, so I'm trying to do this. There are lots of different methods. Some of the most common methods that you might hear about are something called Q-learning. That comes from the reinforcement learning literature in computer sciences. G-estimation was an invention of Jamie Robbins that is kind of amazing, but the literature is super inaccessible, so it hasn't seen nearly as much use as it probably should have. I'm going to focus today on something called dynamic weighted ordinary least squares because it's super easy, so it's my favorite method. And then there's a whole other class of estimators known as value search estimators. The first three that I've mentioned are all regression based. So if you are comfortable with plots like this, you're comfortable with regression, then these methods should be easy to implement. All right, so I'm looking for interactions. Interactions are usually hard to find, right? They tend to be small, which means we don't tend to have a lot of power to detect them. We might see them, but we can't actually say whether they're just there by chance or whether indeed there is some real treatment effect heterogeneity going on there. So when we don't have a lot of power, what do? We look for more data, right? We need big data sets to try to detect small things. So that can encourage collaboration across multiple sites. Using electronic health records is one of the ways we can also get lots of data, and it's easier to do this across multiple sites. But this can raise worries about data privacy. So if we think about, Mireille, I think you're involved in C-nodes, maybe? Oh, you were, okay. So C-nodes is a Canadian network for observational, no, I'm gonna get it wrong. Thank you, drug effectiveness studies. They rely on a lot of provincial level data. But if you look into the details of how the work is done, there is no pooling of the data across provinces. There are analyses done separately in each province. Okay, and that's not uncommon. Sites don't like to share their data for a whole bunch of reasons. One is privacy concerns. Anytime you send data outside of your system, you risk it being stolen or taken by bad actors. Data are also very valuable. You share it for one purpose, but there's no guarantee it won't be used for others, right? So it's sensitive and it's valuable. So there may be concerns about this privacy or data ownership such that sites don't actually want to share their data. So our goal was to see if we could come up with a method that has this nice double robustness property that allows us to estimate these individualized treatment rules without the individual centers actually giving up personal data. All right, so let's look at a one-step setting. I'm in a situation where I have some pre-treatment characteristics. These are things that might be interesting as tailoring variables. They might be interesting as confounding variables. In other words, variables that physicians are using to allocate treatment. So I need to take them into account. I've got some treatment that's received and an outcome that I care about. And I'm going to pretend again that big Y is better. Doesn't matter. If it's not, we stick a negative in front of it and all the math is the same. So I want to try to figure out how to allocate my treatment A for each given X profile to maximize my outcome Y. So if I only had one treatment decision, I could do something as simple as a linear regression. I'm sorry if the colors aren't coming out so well here. So what we've got here is a regression of Y given my covariates X and a treatment A. And what I've got in blue, which I think is not necessarily easy to see at the back, is just an intercept and the main effect of my covariates X. And it turns out it doesn't matter if you can't see the blue because I don't care about this stuff. Okay, that is what we call a nuisance model. I need to estimate it, but it doesn't tell me anything about how to allocate treatment. The stuff I care about is what's in red. Okay, I've got my treatment. I've got a main effect of treatment represented by A times psi, and I've got a covariate treatment interaction. Psi1 times A times, say, a symptom score. So that part in red is what tells me how to allocate treatment. Okay. So we often call this part in red, it's the impact, and we might call it the contrast function. Sometimes it's called a blip function. This bit in blue is just the impact of the covariates at whatever the reference level is of my treatment. It could be at no treatment. If I have two active treatments, it's whatever I pick as the zero level of treatment. All right, so in practice, I specify a model for this contrast. This is the most general form. This is a version of it with one covariate. But actually, I can put in as many covariates as I want. Okay, main effect of treatment, treatment covariate interactions. That's the key. When I specify this contrast in this way, it turns out I have a really simple specification for optimal treatment allocation. Okay, whenever the stuff in brackets is positive, I want to treat with level 1 if I have a binary treatment coded 0, 1. Okay, because I'm trying to maximize my expected outcome. So if this stuff is positive and my only two treatment options are 0 and 1, then I want to keep that positive value. So I keep A equals 1. But if it's negative, I want to get rid of it, right? It's decreasing my outcome where a big outcome is better. Well, I can't turn it positive, but I can set it to 0 and get rid of it. Okay, so I get this linear decision rule where I've got each of my covariates weighted by these psis. I add them up and I check what side of 0 they're on to decide how to allocate my treatment. Okay, so these are known as linear decision rules, and everything I'm going to do today is relying on the pretty strong assumption that this contrast is well specified. Okay, I don't have to specify the other bits I don't care about, but I do need to get that contrast right. All right, so I could just do my regression. I could fit a simple ordinary least squares regression here, get estimates of my psi, and I've got a decision rule based on this. The big but here is, but what if I get that model wrong? What if I don't know how to specify this correctly? It's a complex biological process. Maybe a linear regression is a lousy idea. You know, maybe I don't know how to specify how my symptom score, for example, in the absence of treatment is affecting my quality of life. So what I'd like to do is buy myself a little bit of robustness, buy myself a little bit of slack in the estimation system. And so I'm going to do that by, again, specifying this outcome model, but also specifying a model for how treatment is allocated. So this is sometimes called a propensity score or simply a treatment model. In the binary treatment setting, I can just estimate this by logistic regression or whatever my favorite fitting method is. And now what I'm going to do is fit a weighted regression. Okay, so I'm fitting my simple regression with whatever outcome model I specify, using some weights that follow that, what we call balancing equation. It turns out a bunch of different weights satisfy this. The one that you pick, well, my favorite is this one here with the absolute value because it tends to reduce the variability of my estimates. But inverse probability of treatment weights are something that's quite familiar. We might have seen those from survey sampling literature. They're just as good from the perspective of consistency. They do tend to lead to a little more noise. All right, so what's nice about this method? Well, I have this robustness. If I get either my full outcome model right or my treatment model right, then I can get consistent estimation. Is it easier to get the treatment model right? Maybe. Hopefully, we don't really know. We think it might be because we're trying to understand human decision-making. You can usually solicit from physicians what it is, what variables or information they're using to allocate treatment. It's probably easier to get that right than it is to model a biological system. Let's hope. Okay, it's pretty easy to explain to collaborators. Most clinicians are familiar with regression. You just tell them you're putting in a weight, they're okay with that. We've got lots of generalization, so we can accommodate multiple treatments. It needn't just be binary. We can accommodate continuous doses. We can handle censored outcomes, so time to type outcomes. We have some tools for discrete outcomes, although it's not quite as developed. They're a bit trickier. Okay, and because it's regression-based, who loves regression? We all love regression because it's easy, right? We got to at least regression with one variable at the end of our first stats course. By our second stats course, not only were we doing it, but we saw we had lots of ways of checking it. We had residual diagnostics, we have lots of model selection tools. Okay, so it's got a familiarity and an ease of use and an accessibility that I think is sometimes lacking in some causal literature. The biggest challenge is that we are relying on these linear decision rules. I don't think that they're difficult to use. I don't think they're unappealing, but if we specify them incorrectly, then we could be potentially in trouble. All right, so how do I go about using this if I don't get the real data? I can't get my individual level data. Okay, I want to individualize treatment, but can I? So we looked into some options for obscuring individual level values while still allowing us to estimate these individual treatment rules. There are a lot of different methods that exist for privacy. One of the key ones that you might be aware of is just adding noise to your data, okay? Contaminating the data so that you don't actually see the real individual values. That is not a great idea in this setting because, again, we're looking for these little interactions. And when I say little, I mean it. They're small effects, right? When we add measurement error, we tend to inflate the variance, which again makes it harder to detect the things we're interested in. So we would rather not contaminate the data if we do not need to. So what we looked into were a couple of other options. One is data pooling, so trying to pool information from given centers so that these summaries can be shared. Another is something called distributed regression. It is sort of another form of pooling. I'll explain it in a moment. It's a very different way of sharing the data regression. Data pooling is something that was inspired by actual physical pooling of specimens. It's done in milk. So lots of farms put their milk in one big truck, I guess. They test the truck. If there's no contamination, super. They don't need to go and test for each individual farm. Okay. Same thing has been done. I think it actually started with syphilis testing in the American Army, but I can't remember the exact years on that. It was something that was considered again at the start of COVID when testing was really restricted. Okay, so again, the idea is you stick things physically together in a pool and just test one of them. We're not really testing here, but we are pooling information across samples. Typically, it's done by summing within centers. It can be done across centers, but summing across centers, again, requires sharing data across centers, which is what we're trying to avoid. So this idea of pool size, it's often done on a covariate by covariate basis. I'm going to add up, ages of 5 people, and I will share the sum of these 5 people's ages, and I will do that for lots and lots of groups of 5. But I do it for their age, and I do it for their blood pressure. Every covariate that's of interest, we pool it. Okay? And we can choose this to be done in different ways. So we can have big pool sizes or small. The bigger the pool size, the more privacy, but also the greater the loss of power. It was developed in the context of matched case control studies, the matching allowing for things to be more similar, so there was less pooling to be done. So it wasn't really clear that it would work in this setting. So the idea then is that we want to go from this individual level model to a pooled model where we're summing individual values of the covariates and indeed summing across treatments. Similar approach is used for the treatment model, again, looking at summed versions of these covariates. Okay, so our first idea was, well, that looks like a straightforward procedure. It works well in the matched case control analysis. Let's see if we can just take these small sums. Okay, and again, we have to sum across each of our covariates, do summing again across each of our treatments, and apply our dWOLS, our weighted regression method to this. And we looked at several different strategies. So we looked at pools formed between centers. I will say it's not a great, I mean, it's used in the literature, but I still don't think it makes sense in the context of privacy, because pooling across centers, as I said, requires some sharing of data across centers, which is what we're trying to avoid. We also looked at forming pools within centers, either a fixed pool size across all centers, simplifies things, simplifies the variance calculations, but it does mean you throw out some information unless you happen to have, you know, the same common denominator, so you can get exactly the right size across centers, or looking at different pool sizes, again, formed within centers. The other strategy we looked at is something called distributed regression. This is actually something that comes from a very different literature that's focused on managing high volume data, like streaming data. So lots and lots of data coming in. You just don't want to store all of the original data. We want to find some way to compress that data, so just storing summaries of it. So if we think about linear regression, okay, I'll just do a couple of matrices here. So my linear regression I'm expressing as y is a function of a covariate matrix z and theta. I'm sorry, I know z is a weird one. I was trying not to reuse my x's and a's. So z is just a generic matrix of variables. Theta is a generic parameter. Okay, so I've got my regression. How do I solve that? Z transpose Z inverse, Z transpose Y, right? That's like drilled into us from our first regression course. So I've got two matrices that I need to estimate theta hat. Well, it turns out that if each center just gives me these two matrices, I can sum them and recover exactly the information that I would have had I all the information at once. Okay, mathematically, they're identical. So if I just wanted to do regression, this distributed regression across centers with no weighting, you actually get mathematically equivalent statements or estimators based on summing these two matrices across centers. So it seemed pretty straightforward to apply this in a dWOLS context, although we don't have quite the same equivalence. The reason we don't have the same equivalence is because I'm doing a weighted regression. When I'm doing a weighted regression, I still am passing two matrices from each of the data centers to my sort of central analysis site. But if I had all of the data, if everyone gave me their individual level data, I would estimate these treatment models just once, right? I would use all the data I have to estimate my treatment model or my propensity score, and I would create that weights matrix. But I can't do that. So what's happening is in each site, the treatment model is being weighted, estimated separately. So it's not quite identical, but you would hope that it's not too far off. Okay, so we're not quite getting the same information. It's not identical, but it's similar. So we're using this weighted version of distributed regression to see if we can recover the information that we would have had we been able to have all the individual level data. All right, so let's see how it works. Let's start off with some scenarios where we varied everything under the sun, and don't worry, I don't show you every possible version of this. We looked at having the same covariate distribution across all centers, but also different ones, because often our different sites are different, right? If we think of the C nodes example, the population in Quebec is very different from the population in BC, right? For lots of reasons. So our different sites may not have identical distributions of covariates. We looked at both binary and continuous treatments. We looked at a huge different range of confounding, so the strength at which our covariates predict the treatment allocation. In the pooling, we looked at very different pool sizes from 30 up to 600. And then we looked at different model specifications. So trying to get at this double robustness idea of what can I afford to specify badly? All right, bear with me. The plots are small. We're just looking for big picture. Okay, what you see is everything on a line, right? That's all you need to see. Everything in a line, that's good. Okay, same thing top and bottom. That line that everything is lying on is the truth. Yay, right? It's behaving the way we want it to. So the plots here correctly specify the outcome model, both the interactions and those main effects. I get the regression model right. I know how my covariates affect quality of life. I'm in business. Okay. Over here, I'm incorrectly specifying that outcome process. Quality of life is super complicated. I don't know what's going on, but I know how the doctors give out treatment. I'm getting my propensity score, my treatment model right. And you can see that lots of things fall in a line, but not everything, right? I've got these big bad red spots where things are way off. What's way off is the data pooling. The data pooling is not preserving the double robustness property. So data pooling and the distributed regression work really well when my outcome model is correctly specified, but only the distributed regression is behaving well when I specify the treatment model correctly. Okay, even though I'm estimating it separately at each center, so it's noisy, but it's correctly specified in each center. And then here, everything's off, it doesn't matter, I misspecified everything. We expect things to behave badly when nothing is correctly specified, so we can kind of ignore that plot. But that's really the message here, is that data pooling is not preserving the double robustness that we were looking for. So it's not a good strategy. Okay, we have to get our outcome model right, and we're worried that that's hard to do. We have lots of different options with the data pooling. So even if we thought we could get the outcome model right, there are a lot of pieces of information to keep track of, right? Say I've got 5 potential tailoring variables and another 6 confounders, and I've got my treatment and I've got my outcome. I have to pool each of those for lots and lots and lots of little groups and pass that. So it gets a lot of stuff to keep track of for something that isn't that effective anyway. So it seems like a complex and potentially error-prone solution to this data sharing. The only real advantage of it is, of course, that all you have to do is sum stuff. So if you don't have a lot of expertise in each of your centers, data pooling is useful, but it still doesn't have much to sort of recommend it. The distributed regression, on the other hand, performs really well. Okay, I saw that double robustness. I can get one of my 2 models wrong and still get consistent estimation. We do need some communication between our centers to make sure that everyone is adjusting for the same thing. So if we think about our outcome regression model, we really need the same variables to be in there. Okay. In principle, we could even fit different treatment models. So what I showed you in these results, I was fitting the same treatment model separately in each center, but I don't even need to. If I knew there were different patterns of treatment allocation across my centers, I could accommodate that. So different confounding patterns can actually be accommodated because of these different fits of the propensity score across the centers. And probably the best thing to commend it is that the data are really, really, really highly aggregated. Okay? We're just passing 2 matrices. So we have a high degree of privacy when we're doing this. It does require a little more statistical know-how, though. We have to fit the treatment models, we have to construct the weights, and then we create these matrices that we're sharing. So it does require a little more sort of in-house knowledge from each of our data sites. All right, so we found that this distributed regression approach works well. So we thought, well, what else can we do with this? Can we do even better to account for our confounding by using our center-specific information? So of course, more simulations. We focused in this case on a time to event setting. So censoring involved. Our data generating process assumed that the covariates affecting my treatment allocation and in also the censoring, whether or not we got to observe the outcome, were either common across all our centers or variable, so center specific. And when they were common, we considered settings where both the parameters were common or when they varied. So it could be the same covariates, but different effects across centers. It could be different covariates as well. And under reasonable sample sizes, basically what we found is that locally estimated weights provided better results, right? We would have a little less variability. We would often have less bias by fitting those local confounding patterns. So there you go. Lots of simulations, 1 plot. Okay, so let's look at our case studies then. We start off with one where we have a continuous treatment, so warfarin dosing. Warfarin is one of the most widely used anticoagulants. It's very well understood. Even though it's been around forever and it's really well understood, it's actually really hard to establish good dosing. There is substantial variability in how patients respond. Some of it is genetic. There are a few genetic markers that are known to affect coagulation. There's also within person heterogeneity. Kale, vitamin K consumption affects one's coagulation, which affects how much warfarin you should be taking on a given day. Okay, so even dietary changes can affect how much warfarin one should be taking. It actually turns out that warfarin is one of the leading medications for hospitalizations for adverse events. It's, like I said, it's a great drug for many things, but it is actually really hard to get right. So there's a large trial, data from 11 different centers. I say large, it wasn't that large. Lots of centers, not that much information, where they were trying to target a dosing strategy that would minimize departures from what's known as the international normalized ratio. It's a measure of blood clotting. Right? We don't want too much clotting. If people have too many clots, they can have strokes, they can have heart attacks. We don't want too little clotting because you can bleed. So we want to be right in the middle of this INR range. The target is usually between 2 and 3. So we were trying to minimize departures of the INR from 2.5, right in the middle of the range. Okay, and what we were doing was comparing the coefficients from our regression and the predicted optimal doses from our different privacy-preserving approaches to an analysis that allowed access to the full data. I said we have 11 centers. We actually only use data from 9 because there were a couple of centers that just had very little information. So in a privacy-preserving context, it's very unlikely that a center with 3 people would be willing to share their data. All right, so more pictures that are hard to discern. So what I'm showing in the first 3 plots here are different pooling methods. Okay, and what you see is just a whole lot of noise predominantly. There's a thin increasing line, which is the observed doses. Now, why do I care about the observed doses? Because we know a lot about warfarin, and doctors actually do a pretty good job actually of allocating warfarin doses as it is. So we don't know the truth in this setting, but we think it's not that unlikely that the doctors are doing a good job. So probably we would like to be allocating doses similar to the doses actually given in practice. And what we see with pooling is it's a lot of noise, but it certainly is not tracking closely with what's being given in practice. Our distributed regression, it's better. Not perfect, it's certainly better than the pooling. Okay, and it's tracking more closely to the analysis that we would get if we used all of the individual data rather than our privacy preserving approach. So can I promise you it's right? No, I can definitely promise you that it's better than data pooling. And so if we did need a privacy preserving approach, that's certainly the one that I would recommend. All right, our second case study is looking at a binary treatment. As I mentioned before, I have more than 25 different antidepressants that have been approved for use in the US. These are US data. No, I'm mixing this up. Are these US? Nope, these are my UK data, sorry. This is UK data. So the predominantly given or the main frontline antidepressant is an SSRI, so selective serotonin reuptake inhibitors. So it is the recommended frontline dose. And if you look at what's given out, citalopram and fluoxetine, which are 2 drugs in this class, are by far the majority doses given out for frontline treatment. And so we were looking to see whether we could distinguish characteristics that would make some persons better or worse suited for one of these 2 drugs. So can we do a better job of allocating frontline SSRIs? So we had data from the Clinical Practice Research Datalink, which is a UK data set looking at basically GP data, so general clinical practice. We had data from 10, we call them centers, it was really regions. So we didn't actually have center data, but we did have different regions of the UK, which we treated as centers for the purpose of this analysis. And we wanted to find a treatment rule that maximized the time to a bad outcome. So we don't want a bad outcome, but if you're going to have one, we'd like to delay it as long as possible. Okay, so we were trying to maximize the time to severe depression-related outcomes, where these outcomes included things like hospitalization, self-harm, and suicide attempts. Again, we compared our coefficients and predicted time to outcome under different strategies. So what we found is that the coefficients varied considerably by strategy, whether we were fitting sort of local models or fitting global models. But there was relatively little effect on the predicted time to event. We looked at among those who had these negative events, sort of the median time to a bad outcome was about 42, 43 days on the observed treatment. Not too different if everyone were to be given citalopram, a little bit worse if everyone were to be given fluoxetine. But under our estimated treatment, we delayed these bad events by about a week. So again, it's not a tremendous difference, but it is some delay that is observed, or this improvement that is observed if we could personalize our treatment. All right, so a few final thoughts to wrap up. I think this idea of personalizing medicine just has enormous potential in clinical practice. I will say I've been thinking this for a very long time. I got into this research area when I was a student, and I went and saw a talk by Susan Murphy, and I thought that is the coolest area ever. I still think it's the coolest area ever, and I still think, you know, I'm seeing more of the statistics and medicine collaborating and seeing more of this in practice, but it's still more siloed than it should be. I think that non-experimental data like these big electronic health records and data that are subject to confounding are going to remain a key source. We're still going to need to use these. Of course, randomized data is the gold standard, but we need huge data sets to be able to estimate these effects well. So we have to be really careful in the design of our study base. You know, there are advantages, but we have to be careful. Worry about confounding, worry about all the other challenges that come with these data, like missing information. Generally, selection bias is less of a concern with large observational studies, but it is to be thought about. And of course, privacy is something that we need to think about when we're dealing with large sensitive data, like data about people's mental health. So this distributed regression, I think, offers what I call the almost free lunch. It does give us this privacy protection. It gives us good control of confounding that can be local to different centers, and it's efficient in large samples. We're not losing a lot of information by estimating these extra parameters in the local propensity scores. It does, as it's been implemented, though, assume that that outcome process is global. I'm fitting the same outcome model across all centers, even if I'm fitting local propensity scores. It might be possible to overcome this, but I haven't figured it out yet, although I probably haven't spent enough time on it yet either. As I mentioned, there are a lot of challenges that come from these sorts of data. I think that's not all bad, right? Challenges mean we still have work to do, so it gives us more methodological innovations to work on. So what I'd like to do is briefly thank some of the many wonderful women that I've worked on these projects with. The Warfarin analysis was done with Coraline and Jenny, my former PhD student and postdoc at the back, did the antidepressants data analysis. Susan Shortreed is a collaborator of mine from Kaiser Permanente in Washington. We've been working together on a lot of these ideas for at least 5 years now. And Christelle Renou is also a collaborator here in Montreal at the Jewish General Hospital, who works in these antidepressants and with the CPRD. And I will also take a moment, because I was told I could, since this is the International Women's Day, to talk a little bit about my path. So I promise it's 2 slides, I'll be quick. I am from Winnipeg. I did my undergrad at the University of Winnipeg. When I started there, it was a very small liberal arts college. It's slightly bigger now, but not much. There were about 5,000 students there when I was a student. From there, I flew over to England, where I studied at Cambridge University. I did an MSc or an MPhil in epidemiology, so I got a bit of my health background there before going to Seattle at the University of Washington, where I did a master's and PhD in biostatistics. And then I landed here in Montreal. And some of my inspiration, so this is my family, those are my parents. My dad was a biologist. My mom started as a biologist and in her 40s retrained as a statistician, worked at the Manitoba Cancer Foundation. My dad gets a pass because he makes me statistical jewelry, like my box plot necklace. And this is my sister. I actually followed her to the University of Washington. She's 5 years ahead of me, so she graduated just as I started, but she's also a statistician who works for the HIV Vaccine Trials Network. I mentioned earlier that the whole reason I work in precision medicine was because I attended a talk by Susan Murphy when I was a graduate student. So Susan Murphy and Marie Davidian are probably some of my biggest statistical heroes. I still chat with them, but I still get a little bit big-eyed when I do, because they are just such incredibly intelligent and inspiring women. And I have a whole load of other amazing women that I collaborate and work with. Here and here in the front row, Alexandra Schmidt, who is, I believe, at a conference in Madrid right now, Juliana Schultz, who's at HEC, and again, Susan Shortreed, my collaborator at Kaiser in Seattle. So I also work with some awesome men, but they don't get a nod today. So thank you all so much for your time. Thank you for being lovely women to work and learn and be around.
Thank you very much for this wonderful talk. Do you have questions for our speaker today? I was wondering about the data sampling, because the first case study you showed was like 1,700 people, and then the last one was 200 something, 1,000 something. So you mentioned that it's important to have a large sample. Is this optimal?
Even in the 200,000, we struggle to find anything that was a very significant predictor. I would say I'd like to think that part of the reason it's difficult is because anything that's, I shouldn't say anything, but a lot of the big effects and a lot of the big treatment heterogeneities have been found already. In breast cancer, we know estrogen positive, negative, progesterone positive, negative. So a lot of big effects have already been found. So I'd like to think that we're just looking for what's left, the crumbs that remain. But it is really, it's hard to find anything super dramatic. In most of the studies I've done, we haven't seen much effect of tailoring. There's sort of hints that it's there, but in terms of actual significance or evidence that you would definitely try to deploy this in clinical practice, it's pretty rare. So those huge data sets are definitely more appealing, because at least then you know if you don't see any signal, there's probably no signal there. Whereas with the Warfarin, I'm much more concerned that there may or may not be signal, but we won't find it with so few people.
But is the beta, does the beta need to be, you know, refreshed every now and then? Because how many years can you go back and check for a particular population? Does the situation change?
Right. No, that's a good question. I think it really, it depends on the context in many sense. So for antidepressants, there have not been so many new ones coming on the market. So in some senses, if we don't have new treatments being added, it's less critical. The fact that these are conditional models rather than population average actually helps, because even if there are changing population dynamics, we're really looking at sort of these subgroups. And so as long as we don't have a whole new subgroup entering, you know, so for example, maybe 20 years ago, kids under 12 weren't treated with antidepressants. Now they are. We couldn't use old data to look at that because we simply wouldn't have that subgroup available. So it really depends on the dynamics of the disease and whether there are new treatments coming onto the market or new subgroups who are potentially being exposed to these treatments for different purposes.
You have other questions now that I started?
Could I ask a question as a bias?
Absolutely.
Is this business of modeling and estimating to maximize the time for a bad event? Or it's kind of depressing. Really.
Oh, it's super depressing.
Is that the way problem?
It really varies. In those particular data, part of the reason we did it is because we had measures of hard outcomes like hospitalization, suicide attempts, and so on. We actually also did similar analyses in data from Seattle from my colleague at Kaiser, where there we had softer outcomes, but more positive things. We had things like their symptom scores measured at every clinic visit. So we could do things like try to minimize the time to getting their symptoms below a given threshold or minimize their symptom score. So it really depended on the data availability, but in the UK data, just because of the nature of those electronic health records, we didn't have things like symptom scores. We didn't have any sort of measure of how well they were doing. We just had these really, what can I say, these rather depressing sort of negative but hard measurable outcomes. So it was sort of the most reasonable thing to estimate given the data we had in that setting.
Not that I was curious about the Warfarin example because I didn't actually understand like the tailoring variables INR.
No, sorry, INR was our outcome. We were trying to like minimize departures from the middle of the INR. We had 3 genetic markers: age, sex, we had ethnicity. Sharon, can you remind me, because we're working with those data again? I'll put you on the spot. I'm trying to remember. Those were the main ones, though, because there are 3 key genetic markers that we were looking at. So we were looking at those. I know we had ethnicity, sex, and I can't remember if we had very much else.
Like what's the clinical practice and
So typical practice is based on those genetic markers. They will start you on a higher or lower loading dose. And then there's regular monitoring with doses going up or down depending on those markers. There's actually software that is typically used in practice. It's called the Dawn. I was going to say Dove. It's not. Oh, so no, so they actually take you, like you are brought in regularly every, I want to say it's maybe not quite weekly, but it's on that order until a stable dose is reached. But even then even once a stable dose is reached, there's still frequent but less regular checkups because of these variabilities and things like diet. As I said, the regular practice is to use this Dawn software, which takes it's proprietary. They don't tell us what is used. I've actually got data from Dawn, but it's kind of interesting because even with the Dawn data, physicians override the recommendation roughly 20% of the time. So whatever this optimized algorithm is recommending, the docs on site say, that looks too high or that looks too low. So there's clearly still room to, well, I would think there's still room to optimize unless the doctors are doing a terrible job by overriding it. I don't know. But it's certainly, clinicians have concerns about the algorithms that are in practice. The INR, so INR is a measurement, it's a positive measurement. 2 to 3 is considered the ideal therapeutic range. And so we actually looked at departures from 2.5, right? The closer you are to the middle of the range, the safer you are. And so we were trying to minimize departures from 2.5.
you have repeated measures over time, you can find out.
In this one, we only were looking at the first dose, but for the other data set, which I didn't show you today, we actually do have repeated measurements over time.